In this lecture, I am going to present what is fixed charge and what are the different methods to analyze the fixed charge. Then what is symmetrical fixed charge and unsymmetrical fixed charge. Then how to do the analysis of symmetric parabolic arch. So first coming to the fixed charge. So fixed charge are also called hingeless charge. This is fixed charge. So there are three reaction components at each end of the fixed charge. So the total reaction component is 6. But there are three independent static equilibrium equations are available. So what is the degree of static indeterminacy of the fixed charge? So the degree of static indeterminacy that you can find out by taking the total number of reaction components minus the number of static equilibrium equations available. So the degree of static indeterminacy is equal to 6 minus 3. This is equal to 3. The degree of static indeterminacy is equal to 6 minus 3 is equal to 3. Because here there are three reaction components VA, HA and MA at support A, and at support B there are also three reaction components VP, HB and MB. Total 6 reaction component, and the degree of static equilibrium equation 3. So the degree of static indeterminacy is equal to 3. So this is the typical fixed arch, and this is the degree of static indeterminacy of the fixed arch. Then coming to what are the different methods to analyze the fixed arch. So there are two methods. The first method, this is consistent deformation method, and the second method, elastic center method. So first we will discuss what is about the consistent deformation method. The consistent deformation method is the most basic and most general method. As a first step in the procedure for analysis of propped cantilevers, first remove the redundants and thus reduce the given structure as a determinant one, which is also called a release structure. Then apply these redundants as loads acting on the basic determinant structure. For each redundant we can express one equation. If the degree of indeterminacy is n, then we get n simultaneous equations. After solving the equations, we can find out the redundants. So in this case, what we have to do? So first we have to remove the fixity at the end A. So we will get a cantilever arch, and it is a determinate arch. The cantilever arch is a determinate arch. This one. We will remove the fixity at A. So this becomes the cantilever arch. One end is fixed and other end is free. The cantilever arch shown in figure with the given loading plus the loading VA, H and MA. Here you see this is the determinant arch, this is the given loading, and here this is the reaction, vertical reaction at A, horizontal reaction at A and moment at A. This is the three reactive forces at the support A, and this is the external loading. Basic determinant arch with the forces at the free end, and this is basic determinant arch with the given loading. But we know the net displacement at A is 0. The net displacement, vertical displacement at A, and the horizontal displacement at A, and the moment at A, this is equal to 0. Delta VA is equal to 0, delta HA is equal to 0, and theta A is equal to 0. Where delta VA, delta HA, theta A are the displacement at end A. Delta VA is the displacement at end A, vertical displacement. Delta HA is the horizontal displacement at A, and theta is the rotational displacement at A. Let m dash be the moment due to given loading, and m1, m2 and m3 be the moment due to unit loading in the direction of VA, HA and MA. So let us take m dash is the moment due to the given loading. So what is the loading is present? So if you will find out the moment at any section, so that moment you have to take m dash, that moment you have to take m dash, and let m1, m2, m3 be the moment due to unit loading in the direction of VA, H and MA. So let us take the unit vertical load, unit vertical reaction at A. So due to this unit vertical reaction, what is the moment here? So this is m1, this is m1. So what is the moment here? So this moment you have to take m1. m1 is equal to 1 into the perpendicular distance. First you have to apply the unit vertical reaction at A, and you have to take what is the moment in the fixed charge at a distance x from the support A. So what is the moment here? 1 into x. m1 is equal to 1 into x. m1 is equal to 1 into x. This is equal to x. The moment at a distance x from the support A is equal to m1 is equal to x. Similarly, apply the unit horizontal force at A, and you have to find out what is the moment at a height y from the support A. So what is the moment here due to this unit horizontal force? What is the moment here? So this moment you can denote by m2. m2 is equal to 1 into y. So moment at a height y from the support A is equal to m2. This is equal to y. 1 into y is equal to y. Similarly, apply the unit moment at the end A and find out the moment at any section in the fixed charge. So if the moment at the support A is unit, then at any point at any section in the fixed charge, the moment will remain same. So you will get the moment moment is equal to 1, and that you can denote by m3. So m3 is equal to 1 at any point in the fixed charge. So the moment at any distance from the support A is equal to m3 is equal to 1. So m1 is the moment due to the unit loading in the vertical direction, and m2 is the moment due to the unit loading in the horizontal direction, and m3 is equal to 1. This is the moment due to the moments which is present at the support A. m1 is equal to x, m2 is equal to y, and m3 is equal to 1. m1 x, m2 y, and m3 1. Then find out what is the vertical displacement due to the given loading, and what is the horizontal displacement due to the given loading, and what is the rotational displacement due to the given loading. Similarly, find out what is the vertical displacement, horizontal displacement, and rotational displacement due to the VA, and due to HA, and due to MA. So first we will find out what is the vertical displacement due to the given loading, that you can denote by delta VAO. So using the unit load method, you can find out what is the vertical displacement due to the given loading, and what is the horizontal displacement due to the given loading, that you can denote by delta HAO, HA0, this is delta VA0, this is delta HA0, and the rotational displacement due to the given loading theta A0. So the delta VA0, so as you know from the unit load method, so this is the moment due to the given loading, and this is the unit load present in the vertical direction at the support A, m1. So what is the vertical displacement due to the given loading? So delta VA0 is equal to integration of m dash m1 ds by ei. This is equal to m dash, but you know m1 is equal to x. Here already we have determined, here we know m1 is equal to x, m2 is equal to y, and m3 is equal to 1. So here you put the value of m1. So delta VA0 is equal to integration m dash x ds by ei. Similarly, find out what is the change in horizontal displacement. What is the change in horizontal displacement due to the given loading? Delta HA0 is equal to m dash m2 ds by ei. So m2 you know y, so here you put m dash into y into ds by ei. Then find out what is the rotational displacement due to the given loading theta is 0 is equal to m dash m3 ds by ei, but you know m3 is equal to 1. So after putting m3 1, so the equation becomes integration m dash ds by ei. So this is the change in vertical displacement, horizontal displacement, and this is the rotational displacement due to the given loading. Then find out due to the VA alone. This is the vertical direction at A, this is the horizontal direction at A, this is the moment at A. Due to this vertical direction, what is the moment here? VA into x, VA into the horizontal distance x, VA into x. And due to the horizontal displacement, what is the moment here? HA into y. And due to this moment MA, what is the moment here? MA. So VA into x, this is the vertical, the moment here due to the vertical direction at A. Due to vertical direction VA, what is the moment here? VA into x. And due to this horizontal reaction at A, what is the moment here? HA into y. And due to this moment MA, what is the moment here? MA. Then you find out due to the VA alone, what is the change in vertical displacement. So that you can denote by delta VA1. So delta VA1 is equal to integration of VAx into x ds by ei. This is the moment due to the vertical direction at A, VA into x ds by ei, but after simplification VA integration x square ds by ei. Similarly, what is the change in displacement due to the VA alone? That you can denote by delta HA1. So this is equal to integration VAx into y ds by ei. Then after simplification VA integration xy ds by ei. Then what is the rotational displacement due to the VA alone? Theta a1, that you can denote by theta a1 is equal to integration Vax into 1 by ei into ds. Then VA integration x ds by ei. Similarly, find out due to HA alone, what is the change in displacement, what is change in vertical displacement, change in horizontal displacement, and the rotational displacement. That you can denote by delta VA2 the vertical displacement, delta HA2 the horizontal displacement, and theta to the rotational displacement. So delta VA2 is equal to HA into y x ds by ei, because this is the moment due to HA alone. This is the moment due to HA alone. This is the moment m1. This is the moment due to the HA alone, and this is the moment due to the unit vertical loading, HA y into x ds by ei. So after simplification, HA integration xy ds by ei. Similarly, due to HA alone, what is the change in horizontal displacement? Delta HA2 is equal to integration HA y ds by ei. So then HA integration y square ds by ei. Then what is the rotational displacement? Theta a2 is equal to integration HA y 1 by ei into ds. This is equal to HA integration y ds by ei. Similarly, find out due to the MA alone, what is the change in vertical displacement, and what is the change in horizontal displacement, what is change in the rotational displacement. That you can denote by delta VA3 for vertical displacement, delta HA3 for horizontal displacement, and theta A3 for rotational displacement. So the moment is remains same due to MA alone. So at any section the moment remains same, that is also MA. So what is delta VA3? The delta VA3 is equal to integration MA into x ds by ei, MA integration x ds by ei. So delta HA3 is equal to integration MA y ds by ei is equal to MA integration y ds by ei. Then theta A3 is equal to integration MA 1 by ei ds is equal to MA integration ds by ei. These are the displacement due to the given loading, and this is due to the VA alone, and this is due to the HA alone, and this is due to the MA alone. But from the consistency condition, so the total change in vertical displacement is equal to the summation of these 4 displacement, that is due to the external loading, given loading delta VA0, delta VA1, then delta VA2 plus delta VA3. So the total, the delta V is equal to delta VA0, delta VA1, delta VA2 and delta VA3. And what you know, at the support the net displacement, the change in displacement is 0. There is no displacement expressed at the support. So you have to take delta V is equal to 0. This is due to the external loading, this is due to the VA, this is due to the HA and this is due to the MA. So the change in displacement V, vertical displacement V, delta V is equal to 0. Similarly, the change in horizontal displacement is also equal to 0. So the change in horizontal displacement H, delta H is equal to delta H A0, delta H A1, then delta H A2 and delta H A3. So this is delta H A0, delta H A1, delta H A2 and delta H A3. And the net horizontal displacement at the support, this is equal to 0. Since the rotational displacement theta is equal to integration m dash ds by ei plus va integration x ds by ei plus ha integration y ds by ei plus ma integration ds by ei is equal to 0. So the net displacement delta b is equal to 0 from the consistency conditions. From the consistency condition, delta b is equal to 0, delta h is equal to 0 and delta theta a is equal to 0. So you put the value of VA, VA0, VA1, VA2, VA3 here, and here you put HA0, HA1, HA2, HA3, and here you put theta A0, theta A1, theta A2, theta A3. So the net displacement is equal to 0. The solution of this equation give the value of VA, H and MA. So after simplifying these three simultaneous equations, then you can find out what is the value of VA, HA and MA. These are the three equations from the consistency conditions. Then after simplifying these three equations, you can find out what is the value of VA, HA and MA. Then after getting the reaction at A, the bending moment at any point can be determined using the equation of statics. So after getting the reaction VA, HA and MA, then you can find out what is the moment at any point in the fixed arch. So the moment that you can find out M is equal to M dash plus MA plus VAX plus HAY. So this is due to the external loading, and this is due to the moment at the support A, and this is due to the vertical direction at the support A. This is due to the horizontal direction at the support A. So you can find out the moment at any section in the fixed arch. Then coming to the elastic center method. The elastic center O is defined as the centroid of the analogous column section, the cross section of which is same as the shape of given structure with the thickness at any point is equal to 1 by ei. So this is the fixed arch. So this is the analogous column section. So here also this end is fixed, this end is fixed, and here you have to take the thickness of the analogous column section. This is 1 by ei at any section, that you have to take the thickness 1 by ei. This is the centroid of the fixed arch, analogous column section fixed arch. Then what is the area and what is the centroidal distance and the moment of inertia with respect to any axis. So here this is the x-axis, this is the y-axis of the analogous column section, and this is the centroid. So with respect to this axis and the centroid, so here the area is equal to integration ds by ei, and the ax bar is equal to integration x ds by ei, and ay bar is equal to integration y ds by ei. Similarly, the moment of inertia about the x-axis is equal to integration y square ds by ei, and moment of inertia about y-axis Iyy is equal to integration x square ds by ei, and moment of inertia Ixy is equal to integration xy ds by ei. If the elastic centroid itself is selected as origin, if this is the elastic center, if this is selected as origin, if this elastic center is selected as origin, then x bar is equal to y bar is equal to 0. X bar and y bar, this is equal to 0. If x bar y bar is equal to 0, then integration x dx by ei is 0 and integration y dx by ei is equal to 0. Here you see this is ax bar. If x bar is equal to 0, then integration x dx by ei is 0, and if y bar is equal to 0, then integration y dx by ei is equal to 0. Y dx by ei is equal to 0. If the elastic center taken at the origin, if you take the elastic center at the origin, the consistency conditions are reduced to, after putting this one, integration x dx by ei and integration y dx by ei in this equation, after putting x ds by ei and y ds by ei 0, this is 0 and this is 0, and here x ds by ei is 0 and y ds by ei 0. After putting the value of x ds by ei is equal to 0 and y ds by ei is equal to 0, so the equation reduces to integration m dash x ds by ei plus va integration x square ds by ei plus ha integration xy ds by ei is equal to 0. Then integration m dash y ds by ei plus va integration xy ds by ei plus ha integration y square ds by ei is equal to 0. Then the third equation, integration m dash ds by ei plus ma integration ds by ei. So these are the consistency conditions. After taking the elastic center at the origin, this is the equation. So this is the basic determinant arch with rigid arm or OA. So this is the end A, this is end B, and this is the elastic center. If we will join the support A, the end A and the elastic center O by a rigid arm, if we will join the end A and the elastic center O by a rigid arm OA, so at the end A, the vertical direction VA and the horizontal direction HA and the moment MA. Similarly, at elastic center O, the vertical direction VO and the horizontal direction HO and the moment MO. Imagine a connection between the elastic center O and the end A by a rigid arm. Imagine a connection between the elastic center O and end A by a rigid arm as shown in this figure. Since arm OA is rigid, it will not deform. Hence the displacement component delta V, delta H and theta at point OR are exactly same as those at A. So what is the vertical displacement here? What is the horizontal displacement here? What is the moment here? So that is equal to the vertical displacement at O and the horizontal displacement at O and the rotational displacement at O. As the rigid connection is connected between the O and A. Then the equations at O, elastic center, what is the vertical displacement? Here the equation becomes at support A, so the equation is, this is the equation, at support A, this is the equation. But when the imaginary connection is connected between the center O and A by a rigid arm, and here also the expression is same as you got from the support A. So here also the equations, integration m dash x dash ds by ei, integration m dash x ds by ei plus VO integration x square ds by ei plus HO integration xy ds by ei. Only you have to replace, instead of A, you have to replace the O, VO, HO and MO. The second equation, integration m dash y ds by ei plus VO integration xy ds by ei plus HO integration y square ds by ei. And the third equation, integration m dash ds by ei plus m0 integration ds by ei at the elastic center O. These are the equations at the elastic center. Then coming to what is symmetrical fixed arch. So this is a fixed arch and this is the symmetrical fixed arch, because the center is here, this is the vertical axis and this is the horizontal axis. Here the fixed arch is symmetric with respect to the y axis. Here the fixed arch is symmetric with respect to y axis because this side is equal to this side. So in this case, the moment of inertia Ixy is equal to integration xy ds by ei is equal to 0. So in the case of symmetrically fixed arch, the moment of inertia Ixy is equal to integration xy ds by ei is equal to 0. Then after putting this value here in this equation, here integration xy ds by ei is 0, and here also integration xy ds by ei is 0. So after putting this value 0 and this value 0, the equation reduces to, this is the final equation. The integration m dash x ds by ei plus b0 integration x square ds by ei is equal to 0. Then the second equation m dash y ds by ei plus h0 integration y square ds by ei is equal to 0. Then the third equation m dash ds by ei plus m0 integration ds by ei is equal to 0. From these equations, you can find out what is the moment MO, VO and HO. What is the moment MO, what is the vertical direction VO, and what is the horizontal direction HO at the elastic center O. So you can find out this here. VO is equal to, take this is opposite side, minus integration m dash x ds by ei divided by integration x square ds by ei. So this is the VO. Similarly MO, so you can find out MO from this. MO is equal to minus integration m dash ds by ei divided by integration ds by ei, this one. Then HO you can find out from this relation. HO is equal to minus integration m dash y ds by ei divided by integration y square ds by ei. So these are the moment, vertical direction and horizontal direction at elastic center O. So this VO, HO and MO can be evaluated using this equation. Then after knowing VO, HO and MO, the moment at any point can be determined by static equilibrium equations. So after knowing VO, HO, MO, then you can find out the moment at any point using the static equilibrium equations. Then what is unsymmetrical fixed arch? So in the case of unsymmetrical fixed arch, so this is the elastic center. So here the moment of inertia Ixy is not equal to 0. If the arch is unsymmetric, Ixy is not equal to 0. Integration xy ds by ei not equal to 0. So this case you can find out. So from this relation you can find out what is the VO, HO and MO, because here the xy ds by ei is not equal to 0. So MO is equal to minus integration m dash ds by ei integration ds by ei. Then VO is equal to minus integration m dash x ds by ei minus integration m dash y ds by ei into integration xy ds by ei divided by integration y square ds by ei, divided by whole divided by integration x square ds by ei minus integration xy ds by ei divided by integration y square ds by ei. Similarly h0 that you can find out from this relation. So you can find out m0, v0, h0 for the unsymmetrical fixed arch. From this equation you can find out what is the moment at the elastic center, what is the vertical reaction at the elastic center, and what is the horizontal direction at the elastic center for the unsymmetrical fixed arch. Then coming to analysis of symmetric parabolic arch. This is symmetrical parabolic arch. So here this is the elastic center and this is the crown. This is the x-axis, this is y-axis. Consider the symmetric parabolic arch, crown C at the origin. If you are taking crown C at the origin, so what is the equation of parabola? The equation of parabola is y dash is equal to a x dash whole square, where a is the constant. But what is the value of x dash? X dash is equal to L by 2. The x dash, this is the x dash. If you are taking, this is the origin, crown of the origin. So this is the x dash. X dash is the total length of the parabola is The total span of the parabola is L, and what is this length? X length, X dash, this is X dash and this is Y dash. So X dash is equal to L by 2. And what is Y dash? Y dash is equal to minus H. X dash is equal to L by 2 and Y dash is equal to minus H. Then after putting this X dash and Y dash here, so we will get H is equal to minus A L by 2 whole square. Then after simplification, you will get A is equal to minus 4H by L square. Then after putting the A value here in the parabolic equation, Y dash is equal to AX bar square. So here you have to put A value. So after putting this one, Y dash is equal to minus 4H by L square into X bar X dash square. This is the Y dash. This is the relation between the Y dash and X dash. And this is the equation of the parabola in the case of symmetric parabolic arch. Because of symmetry, the elastic center lies on the symmetric y axis through C. Let it be YC below C. The elastic center lies on the symmetric y axis through C. The elastic center lies in the y axis through C. This is the crown. So this is the vertical y axis, and here the elastic center lies just below the C, below C in this axis. Let it be YC below C. So the distance from the C to O, this is the distance YC. AYC is equal to integration y dash ds by EI. This is the relation you know, AYC. Then YC is equal to integration y dash ds by integration ds by EI, because area is equal to integration ds by EI. If the parabolic arch has I is equal to I0 sec theta, then after putting I is equal to I0 sec theta in this equation, the equation becomes YC is equal to integration y dash ds by EI0 divided by integration ds by EI0. This is the YC value. This is the distance between the crown and the elastic center, C and O, YC. So the YC that you can find out, because this is the YC, this is YC, this is YC. Then you have to put here y dash. You got here the y dash value. Y dash is equal to minus 4H by L square into X dash square. So here put here. So after putting this value y dash, so you get YC is equal to 0 to L by 2 minus 4H by L square into X dash square into dx divided by 0 to L by 2 into dx. This is for the whole parabolic arch for both sides, because you are taking the crown at the origin, so you have to take this side 0 to L by 2 and this side 0 to L by 2. So you can, after integrating, you can find out what is the value of YC. So YC is equal to minus H by 3. So this is the value YC, that is the distance between the crown and the elastic center equal to YC, and this value is equal to minus H by 3. What is the height of the parabolic fixed arch? So the height by 3 is the YC value. In the case of symmetric parabolic arch, the elastic center lies on the symmetric axis at H by 3 below the crown. If the elastic center is taken as origin, the equation of the parabola will be y is equal to YC minus 4H by L square into X square. Then after putting YC is equal to H by 3, so y is equal to H by 3 minus 4H by L square into X square. Using this equation for parabolic arch, the value of M0, V0 and H0 at the elastic center O may be determined. Then the moment at any section may be determined using the equation of statics. You can find out the moment at any section using the equation of statics after getting the M0, V0, H0 at the elastic center. Now all are clear. What is fixed arch and what are the different methods to analyze the fixed arch? Then what is symmetrical fixed arch and unsymmetrical fixed arch? Then how to do the analysis of symmetric parabolic arch.